Alright guys, we're continuing the lesson on momentum. So we did worksheet 1 before, and to just summarize worksheet 1, we learned about momentum. All objects, if they are moving, have momentum. It's a combination of mass and velocity, and it's a linear relationship. You double the mass, you double momentum, you double velocity, you double momentum. If velocity is 0, you have no momentum. So you need to be moving for momentum. We kind of went through a lot of scenarios. Now I'm going to have us do the simulation lab. So the easiest way, you could just type in PhET collision lab. If you want, you can open up this link, but either way, open the link, PhET collision lab. I'll even show you if you type into Google, that'll be PhET collision lab, and it should be this first link here. Open up what looks like this video, and then go to the intro. So we're basically looking at two scenarios here. So if we look at this worksheet, we're going to look at what we call an elastic collision and an inelastic collision. And the way I switch from that is I'll say this either be 100% elastic or 0% elastic, which means you're inelastic. Let's start with what it normally is default is at 100%. So I'm going to have these two objects go and collide with each other. So let's break down what's happening here. Object 1 is moving towards Object 2. It's moving faster. Object 2 is moving towards Object 1. It's going slower. Object 1 is less mass than Object 2. And right before they hit is what they look like. And after look like that. So they're going opposite directions. So what we want to break down first is what was their combined kinetic energies beforehand. And we can go through all the work to figure this out, but we can actually, let's just put on here, I'm just going to hit kinetic energy here. And so the kinetic energy of the system, and it's these two guys combined, is equal to 0.44 joules. And I'll ask you, if you want to see before and after, like how we get this number, if I calculate the 1/2 mv squared for object 1 plus the 1/2 mv squared for object 2, I will get 0.44. And I notice after it's the same amount. So I'm going to go back here. So EK before is equal to EK1 plus EK2. And, I'll tell you now, this is how you would get 1/2 m1v1 squared plus 1/2 m2v2 squared. Now, some people will ask, like, well, object B is going to the left, object 1 is going to the right. So I'll show when they start, they're going opposite directions. Should their kinetic energy, should one be negative, one be positive? Because velocity would be the negative one, since you square velocity, two negatives multiplied into each other become positive, you'll still end up with two positives adding up into each other, and you'll get 0.44 joules. Now I'm going to do the EK after, which is going to be EK1 prime plus EK2 prime, which if we're going to break it down, and I'm just skipping the math of it because it's going to take a long time, but what you will notice here, and what our simulation even tells us, is that I still maintain this 0.44 joules. So what's happening here? So essentially what we've had happen is that these objects, it seems like they hit each other and our energy is conserved, which is what we're used to in the previous unit. In the previous energy unit, we dealt with that. Now I'm going to make these momentum, I'm not going to do the full bar charts, but I'm going to write out my momentum equation. So P before is equal to P after. Remember, P represents momentum. I'm going to do momentum 1, so P1 plus P2. And how does that relate to P1 plus P2 prime? I'm just going to use the numbers they give me here. I'm just going to go real easy. The way you would get these numbers is M1V1 for every scenario. So mass 1 of the velocity 1 before. Primes always mean after. Let's see what we get. 1. So I'm looking at this. If I count the mass and the velocities here, let's just see what we get. 1, 0.5 times 1, I get 0.5 kilogram meters per second. 1.5 times negative 0.5, I get negative 0.75. All right, so I'm just showing y'all how you would calculate that. So I have 0.5 minus 0.75 equal to, let's let them collide. And afterwards, I get negative 0.63 and positive 0.38. If I combine all these, I get negative 0.25 as my overall system momentum. And this should be the same amount. Now, if you plug this all in, you should get also negative 0.25. And look at that, the momentum before is equal to the momentum after. So what I've concluded here, in elastic collisions, we have what we call conservation of energy. Energy before is equal to energy after. Conservation of momentum is also true, which is the same thing but for momentum. Momentum before is equal to momentum after. So both are true. Let's do the exact same thing for inelastic, and actually I'll have y'all do this. I'm gonna reset it, make the slider go down to 0 elasticity, so now it's inelastic. I'll let you see the difference here. So y'all play around with it, do what we did before, and see what you get. So here I have them hit each other, and look at that. Instead of bouncing apart, they're actually stuck together now. So, all right, I'm gonna fill out all the information beforehand so I don't make this video really long. When I analyze the kinetic energies before and after, I notice I go from 0.44 to 0.02 joules. And we figured out the energy the same way as before, but I notice now these are not equal. So not equal. I lost 0.42 joules. That's interesting. Let me look at the momentum now. So I'm going to reset this. Let's look at the momentum before. I start off the same way. I have, so P1 plus P2 equal to P1 prime plus P2 prime. I have 0.5 minus 0.75 is equal to, after they collide, negative 0.06 minus 0.19. And if I add them up, I get negative 0.25 is equal to negative 0.25. So what is the whole conclusion of all of this simulation? Conservation of energy is not conserved, meaning EK before is not equal to EK after. However, conservation of momentum is conserved. Momentum before is equal to momentum after. And I'm going to go one step further. I'm going to actually clarify. When I say momentum before, I mean the combined momentums of both objects before collision is equal to the combined momentums of both objects after collision. So basically what I've seen here is that I can always trust conservation of momentum in collision equations, but I can't always trust conservation of energy. So in the next worksheet, we'll see how that plays a role in this.